Welcome back to Calculus 2. In this section, we will see a very cool application of integrals to solve physics-based problems. We will use integrals to calculate the amount of work performed in various situations. So as we begin, let's think of the basic formula for work. If we have work that's performed by a constant force, let's just say the force is F, as long as the force acts parallel to the displacement, if it moves an object a displacement, or a distance, of d, then the work is given by work equals force times distance. We can think of work as measuring the cumulative effect of the force over the displacement of the object. Now, in order for this formula to be applicable, we need to have a constant force, we need to have a fixed distance, and the force must be acting parallel to the displacement. Now, before we get any further, let's review some important physics concepts that will be used in this section. Mass is the amount of matter that an object contains. The mass is constant no matter where the object is, whether it's on the Earth or the Moon or wherever. Mass is constant because it's just measuring the amount of matter contained in the object. Weight is a measure of gravitational force, and this changes based on whether an object is on the Moon or on the Earth, or it even changes with elevation above the Earth. And weight can be calculated by taking the mass times gravitational acceleration. We use g as the symbol for the gravitational constant, and we'll use 9.81, and the units here are units of acceleration meters per second squared. Often in this section, forces will be corresponding to weights of objects. So a weight is a measurement of force, and oftentimes forces involved here are weights. When we solve problems in this section, it's important to always keep track of units. We'll often deal with different densities here, which is typically a measurement of mass divided by volume. And sometimes we'll deal with something called a weight density. So it's important to distinguish between mass density and so-called weight density. And using units will help us to distinguish between these two quantities. So units for force, the standard metric units are kilograms times meters per second squared. We have mass times acceleration. And if we think of how to get weight based on mass, we multiply mass times gravitational acceleration. So that's the metric units of force. The imperial units are pounds. Now work, remember the basic formula for work. For a constant force, we have work equals force times distance. So for metric units, we have force, that's measured in newtons, times distance, which is measured in meters. Newtons times meters is the unit joules. So joules is going to be the standard measurement here. For metric, for the imperial system, we will measure work using foot-pounds. We can think of a foot-pound as the amount of energy required to move an object that weighs 1 pound, a distance of 1 foot. Now that we've reviewed some of these physics concepts, let's take a look at an example. In example 1, we have a crane that is lifting a 500 kilogram beam 40 meters into the air. We want to know how much work has the crane performed. So let's draw a little picture here. We have a beam that weighs 500 kilograms. Actually, we shouldn't say weighs, the mass is 500 kilograms. And the crane is moving the beam a distance of 40 meters into the air. This is a constant force. The force is just the weight of the beam, and the distance is 40 meters. So we can use the work formula, work equals force times distance. Force is the weight of the beam, and we can find the weight of the beam by multiplying kilograms times the gravitational constant. So we take 500 times 9.81 times the distance, which is 40 meters. Now let's keep track of units as we do this. 500 is kilograms, 9.81 is meters per second, and 40 is units of meters. When we take kilograms times meters per second squared, that gives us units of newtons. And then newtons times meters, altogether we have units of joules. So the units are correctly working out here. We have kilograms times meters per second squared times meters. This is newtons times meters. That gives us joules. All right, and if we plug this into a calculator, we'll get the final answer. which is 196,200 joules. That's how much work has been performed when the crane lifts this 500 kilogram beam a distance of 40 meters into the air. We could use this formula because we have a constant force, which is just the weight of the beam, and it's being moved a constant distance of 40 meters. Now, what happens if we don't have a constant force? What if the force changes throughout the object's displacement? Or what if the displacement of the object is different for different places of the object? Well, that's what we'll focus on in this section. So we want to focus on problems where either the force is not constant, or problems where the displacement is not always the same. We will be able to handle both of these situations using integration. And it's important to understand the philosophical idea behind why this works. Here's a big idea for us to understand as we think about this section. The key for solving these problems is to find an expression for the work performed on a representative slice. This is very similar to concepts that we saw when we were finding volumes. If we wanted to find the volume of a certain shape, we first sliced it up and tried to find the volume of a representative slice, and then we integrated to find the total volume. We do the same sort of thing here. We find the amount of work performed on a representative slice, and then to find the total amount of work, we integrate. It is critical to be able to think of the problems in this way as we go through this section. So let's think of work performed by a variable force. If we have a variable force given by a force function f of x, as long as the force again acts parallel to the displacement, if it moves an object from x equals a to x equals b along the x-axis, then we can find the work using an integral. Here's the formula, and after we write down the formula, let's talk about where it comes from. Work is equal to the integral of the force function from a to b. Isn't this an elegant formula? I mean, we have just such a clean, simple integral expression to calculate the amount of work done by a variable force. I think this is such a nice, neatly packaged formula for us to use. Now, let's talk about why this formula is true. Can we verify why work performed by a variable force is just equal to the integral of the force function? Let's draw a picture and see if we can figure this out. So we're moving an object along the x-axis. So here we have the x-axis, here's the origin, and we're moving the object from an x value of a to an x value of b. Now the force changes as the object moves from a to b. So maybe at the start, maybe there's not much force applied, and then maybe further on there's more force, and then maybe it lessens. We really don't know. We just know that as the object moves from a to b, the amount of force that's being applied will change. So it's important to realize here that we can't use the formula for work that we're used to. We can't just use work equals force times distance because the force changes. What force would we use if we were to use this formula? Well, we can't. The force changes throughout the region here. So the way to handle this is to imagine taking just one small portion of the displacement. We want to imagine what happens over a small change of distance here. We're going to take a slice of displacement. It sounds strange to say that, but we're just going to take a representative slice of displacement here. And since we're along the x-axis, we'll call the width of this slice dx, some small change in x. And we want to know how much work is performed when the object is moved over this small piece of displacement. Now, the force function is variable. The force changes over this entire distance here. But for just a small change in displacement, we can approximate the force as being constant. That's the whole key here. For this small bit of distance, we can pretty much assume that the force is constant. So we're at some distance x from the origin. So the force here is the force function at the distance x. So we're moving the object over this small bit of displacement. The distance that the object is moved is dx. The force being applied is f of x, and we can approximate this as being constant since we're moving over just a small displacement. So now we can write an expression for the work performed on the slice. So this small bit of work we could actually call dW to just represent a small amount of work over this small bit of displacement. So dW, that's the work performed for that slice. It's force times distance. So we have force times distance. And then in order to find the total amount of work, we add up all of the representative work from A to B. How do we add up all these infinitesimally small pieces of work? We integrate. So the total work, we integrate dW, and we have the integral of dW, which is the force function, dx. Integrate from A to B, and that effectively adds up the total amount of work over the entire interval from A to B. So here's our formula. For a variable force, work equals the integral of the force function. Let's work through a couple examples where we apply this formula. Take a look at example 2. Hooke's law says that the force applied by a spring is proportional to the distance the spring is compressed. In other words, the force of a spring compressed to distance x is given by this function here. The force is proportional, there's a constant of proportionality k, to the distance x that the spring is compressed. Now, if you think about this, this kind of makes sense. Imagine taking a spring, maybe like the spring from a ballpoint pen or something, and imagine trying to compress the spring. At first, it's relatively easy. There's not really much resistance. But the more you compress that spring, the more of a force is required to hold it compressed. So the force varies with the distance that you compress the spring. And Hooke's law tells us how much the force varies. It says that the force is exactly proportional to the distance that the spring has been compressed. So let's take a look at part A. We have a spring that started at rest and was compressed 0.2 meters. The spring constant here is 10. We want to calculate how much work was performed when the spring was compressed 0.2 meters. So we'll imagine drawing a spring here, and then the spring is being compressed 0.2 meters. So I'm going to draw a slightly more compressed spring, and it's been compressed 0.2 meters. The force function for a spring is f of x equals k times x, and we're told for this problem that k equals 10. So this is 10 times x. It's important here to understand the distinction between force and work. Force and work are two different things. Force is telling us how much pressure, if you will, or how much force is required to compress the spring and to keep it static in place. If we were to think of compressing this spring and to keep it from moving at all, then the force required would just be 10 times 0.2. So we could actually calculate that. The force to keep this compressed, this would be F of 0.2, which is 10 times 0.2, so that's 2 newtons. And this is a static quantity. This is keeping the spring just compressed from moving at all. And if we were to compress it further and keep it static there, then it would require more force to keep it from moving. Work, on the other hand, is calculating the force over this displacement. So we're calculating starting from rest and compressing it this much. What's the overall accumulation of the force? So the work formula here, since we have a variable force, work is the integral of the force function. So we're integrating the force function. And what are the limits of integration a and b? Well, we start at rest. So we'll start with a equals 0. And b is the distance that we're compressing, 0.2. And the force function is 10x. So here's our expression for the total amount of work performed when we compress the spring a distance of 0.2 meters. Let's go ahead and calculate this integral. The antiderivative of 10x is 10x squared divided by 2, so 5x squared. We're integrating from 0 to 0.2. We plug in the upper limit, 0.2. 0.2 squared minus 5 times 0 squared, so that's just 0. 0.2 squared is 0.04. 5 times 0.04, this gives us an answer of 0.2. The units here are joules, newtons times meters. So the total amount of work performed here is 0.2 joules. That's the amount of work performed as we compress the spring a distance of 0.2 meters. Let's take a look at problem 2b. We're working again with a spring, but notice that the units here are going to be imperial. We're working with feet and pounds, so work will be measured in foot-pounds. So suppose the force necessary to keep a spring stretched by 0.2 feet from rest is 10 pounds. So again, this is static. If we imagine taking the spring and stretching it, we're applying 10 pounds of force to keep it statically stretched a distance of 0.2 feet. We want to know how much work will be done if the spring is stretched from rest a distance of 0.6 feet. Now, what we don't have for this problem is the value of the spring constant. So we're going to use this first piece of information to find what the spring constant is for part B. And then in order to find total amount of work done, we will just set up an integral. So first of all, we know that the force function has the form f of x equals some constant of proportionality times x. In this problem, we do not know the value of k, but we do know that when the spring is stretched 0.2 feet, the force being applied to keep it statically stretched is 10 pounds. So that tells us that f of 0.2 equals 10. Well, 0.2 is the value of x here. So if we replace the x with 0.2, we know that this is also equal to k times 0.2. This allows us to solve for the spring constant k. Divide both sides by 0.2, we have k equals 10 divided by 0.2, which is 50. Now that we have the spring constant k, we're ready to solve the rest of the problem. So we want to know how much work is done to stretch the spring 0.6 feet. Well, work equals the integral of the force function. So we're integrating the force function from a to b. If we stretch the spring from rest, then we start at a distance of 0, and we're stretching by 0.6 feet. We have 50x as the force function. And we'll go ahead and leave the integral just like this. If we evaluate that, well, we'd have to find the antiderivative of x, which is x squared divided by 2. We could easily work through that. And the final answer here, if we evaluate the integral, is simply 9. The units are foot-pounds.